Pluto is a distant, elusive, and unassuming world that once belonged to our solar system's planetary lineup. But recent, unsettling declarations by prominent astrophysicists like Neil deGrasse Tyson and Michio Kaku have revived interest in this cold planet. They have suggested that Pluto might be on a potential collision trajectory with Neptune. But how might this be possible, and what could the consequences of such an immense event be? Are we witnessing an overwhelming astronomical anomaly, or is there more to this emerging cosmic dilemma? Join us as we explore the possible outcomes of a Pluto-Neptune collision. Pluto, which was once classified as a planet but later redefined as a dwarf planet, remains a captivating subject for scientific exploration. As highlighted by recent forecasts from leading experts, Pluto's orbit is dangerously close to Neptune's, and both Tyson and Kaku have raised concerns over the potential for a catastrophic encounter between the two. But how could this event occur? Pluto's journey around the Sun is unlike that of any other planet in the solar system. It takes an extraordinary 248 years to complete a single orbit, and since its discovery in 1930, it has yet to finish a full cycle. Despite this, the intrigue surrounding Pluto doesn't end there. The planet's orbit is characterized by a highly elliptical trajectory, drifting far from the nearly circular orbits of the major planets. What makes Pluto's orbit even more unusual is its inclination of 17 degrees to the ecliptic plane. This distinctive path makes Pluto's orbit far more erratic compared to those of other planets, adding complexity to its cosmic arrangement. One of the most intriguing aspects of Pluto's orbit is its intersection with Neptune's. For a period of approximately 20 years during each orbit, Pluto actually moves closer to the Sun than Neptune, defying conventional expectations about their relative positions within the solar system. This raises the natural question: why hasn't Pluto collided with Neptune yet? The answer lies in the gravitational forces exerted by other planets. Soon after Pluto's discovery, astronomers began studying its unique orbital behavior. Unlike the relatively stable orbits of other planets that lie close to the ecliptic plane, Pluto's path stood out because of its steep inclination and erratic shape. The mystery deepened when it became clear that Pluto's orbit crosses Neptune's. However, the stability of Pluto's orbit, despite these peculiarities, is a testament to the complexities of celestial mechanics. The three-body problem, which involves predicting how three objects in space, such as Pluto, Neptune, and the Sun, move and interact under the influence of gravity, is essential in understanding the delicate balance that prevents collision. It's akin to trying to predict their future positions based on their starting points and how their gravitational forces pull on each other. In Pluto's case, the three-body problem demonstrates how its orbit, Neptune's orbit, and the Sun's gravitational pull work together in a highly intricate way. The concept of non-concurrent libration, orbital precession, and VZK wobbling are critical to solving this puzzle. According to astrophysicists, non-concurrent libration is what prevents Pluto and Neptune from colliding. Essentially, when Pluto crosses Neptune's orbit, it remains at least 90 degrees apart from Neptune, a spatial division that ensures the two orbits do not intersect. Orbital precession, on the other hand, refers to the vertical movement of a body in its orbit. For Pluto, this means that when it comes close to Neptune or any other large planet, it is positioned far above their orbital plane, providing an added layer of protection from potential collisions. Another crucial factor in this equation is the VZK wobbling, named after three researchers, Zell, Kai, and others, who investigated how objects move in space. The wobbling refers to how Pluto, Neptune, and the Sun exert gravitational forces on each other, influencing their movement. For Pluto, this phenomenon helps explain the unusual nature of its orbit, even as it remains stable over long periods. Despite Pluto's orbit seeming chaotic at first glance, this gravitational interaction maintains a balance, ensuring it doesn't collide with Neptune or veer off course. The three-body problem is vital for understanding how orbits evolve and change due to gravitational forces. Studying this dynamic helps us not only learn about Pluto's path around the Sun, but also provides insights into the broader behavior of distant worlds and their stars. In the late 1980s, numerical simulations revealed that despite the stabilizing factors, Pluto's orbit is still somewhat erratic, with small deviations in its initial conditions leading to significant changes over centuries. However, these irregularities in Pluto's orbit have been shown to maintain long-term stability, offering hope that the delicate cosmic balance will persist. The influence of Neptune, Jupiter, and Saturn in stabilizing Pluto's orbit is especially noteworthy. For example, there is a specific relationship between Pluto and Neptune, For every 2 orbits Pluto completes around the Sun, Neptune completes 3. This synchronization helps stabilize Pluto's orbit, but Jupiter's massive gravity plays an equally vital role in maintaining its path. Saturn also contributes to Pluto's orbital stability. Studies indicate that Jupiter's enormous gravity is sufficient to ensure Pluto's orbit remains steady for millions of years, potentially preventing catastrophic events. In essence, Neptune, Jupiter, and Saturn work in concert to ensure Pluto's safe passage through the cosmos, minimizing the risk of a collision with Neptune. These peculiarities of Pluto's orbit are crucial for maintaining stability in the solar system. Without these stabilizing mechanisms, the solar system would be a far more chaotic and volatile place. Bodies like Pluto could collide with other celestial objects or be ejected from their stable orbits, potentially triggering a domino effect of collisions across the system. Thus, understanding Pluto's orbit is crucial in assessing the potential risks of a future collision with Neptune and shedding light on the dynamic nature of our cosmic neighborhood. The case of Pluto exemplifies how even the most seemingly unstable orbits can achieve a form of balance over time through the complex interaction of gravitational forces and orbital mechanics. It also underscores the importance of continual observation and study of these cosmic phenomena to better understand our place in the universe. Space exploration often brings us face to face with the mysterious and irregular nature of celestial bodies, and Pluto's orbit is a prime example of such anomalies. The concept of orbital chaos, which describes how a celestial body's orbit depends on its initial conditions, is clearly illustrated by Pluto's path. Even slight changes in Pluto's position or speed can lead to dramatic shifts in its long-term orbit. Automated simulations have been incredibly valuable in helping scientists understand Pluto's movement through space. These simulations use sophisticated mathematics to model how Pluto interacts gravitationally with other objects like Neptune. By adjusting minor details in these simulations, researchers can observe how small changes can dramatically impact Pluto's future trajectory. In the late 1980s, simulations revealed that despite Pluto's stabilizing factors, its orbit remains unpredictable and can vary dramatically depending on initial conditions. This chaotic behavior underscores the challenges in predicting Pluto's future path. Even slight changes in Pluto's speed or location can alter its orbit significantly over a relatively short time span. Yet, despite these chaotic tendencies, Pluto's orbit remains relatively stable over vast time scales, including billions of years. This suggests that there is an underlying order to its journey around the Sun, even though its path may appear erratic at times. Predicting the movements of celestial objects with irregular orbits, such as Pluto, presents enormous challenges due to the inherent unpredictability of these systems. While numerical models provide valuable tools for understanding and predicting celestial movements, they also highlight the limits of our ability to make precise long-term forecasts. Small errors or distortions in our understanding of initial conditions can lead to vastly different outcomes, making accurate predictions difficult. In addition to the chaotic nature of planetary orbits, Pluto serves as a reminder of the constantly shifting and dynamic universe in which we live. While we've made tremendous progress in understanding space, Pluto's case demonstrates how much remains to be discovered. By grasping the gravitational interactions between Pluto and the giant planets, we gain important insights into the broader workings of our solar system. The position and mass of each planet significantly affect the stability and movement of other bodies, helping maintain the overall balance of the system. Despite the intricate gravitational forces that work to prevent a collision between Pluto and Neptune, leading astrophysicists are increasingly concerned about the potential for such an event. Neil deGrasse Tyson, a renowned astrophysicist and key figure in the reclassification of Pluto, offers valuable perspectives on the mysteries of our solar system, especially the unique case of Pluto. Tyson views the reclassification not as a diminishment of Pluto's importance, but as an adjustment based on the growing body of knowledge about our solar system. He emphasizes that the complexities of orbits like Pluto's reveal just how much there is still to learn about space. However, despite his optimism, Tyson has expressed concerns about Pluto's potential collision with Neptune in the distant future. He explains that as the solar system continues to evolve, the gravitational dynamics between planets like Pluto and Neptune can slowly change over time. Although the likelihood of an immediate collision is extremely low, Tyson and others warn that such an event could occur over billions of years, should small shifts in gravitational forces cause instability in the system. Tyson's analysis also highlights the fact that while the current dynamics between Pluto and Neptune are stable, we must account for the long-term implications of their orbits. Even slight changes in gravitational forces could disrupt the balance that prevents a collision. The possibility of a Pluto-Neptune collision, though rare, underscores the fragility of celestial mechanics in our solar system. Tyson's comments emphasize the ongoing evolution of the solar system, where even minor adjustments to the orbits of massive planets like Neptune, Jupiter, and Saturn could eventually destabilize Pluto's orbit. While the delicate balance that currently exists between Pluto and Neptune helps avoid direct collisions, there is always the potential for this equilibrium to shift over millions or billions of years. This makes Pluto's orbit a dynamic, ever-changing puzzle where everything must align perfectly to prevent catastrophic consequences. Nonetheless, despite the potential for future changes, it is important to recognize that our understanding of the solar system is still developing. As technology improves, new models and simulations offer deeper insights into the long-term stability of planetary orbits. Future observations could reveal even more about how planets interact over time, providing better predictions and potentially offering solutions to these cosmic mysteries. In conclusion, although the prospect of a Pluto-Neptune collision seems highly improbable in the near future, studying their orbits provides a fascinating look into the dynamic nature of our solar system. The intricate gravitational relationships between planets and dwarf planets like Pluto reveal the delicate balance that governs space. Even the slightest shifts in these forces can lead to significant changes over time. Astrophysicists like Tyson continue to investigate these mysteries, reminding us that the universe is in constant motion and our understanding of it is continually evolving. As we look toward the future, the study of space will remain an exciting field of discovery, one filled with new surprises, questions, and revelations. The study of Pluto and its relationship with Neptune serves as a profound reminder of the intricate dynamics that shape our solar system. Despite the seeming tranquility of their current orbits, the forces at play between these two celestial bodies highlight how small, unnoticed shifts can accumulate over vast stretches of time. While current models suggest that the possibility of a collision is minimal, the universe is full of unexpected phenomena, and what may seem stable today could evolve into something far more unpredictable tomorrow. As astrophysicists continue to refine our understanding of Pluto's orbital behavior, they are also enhancing the broader understanding of the forces that govern planetary and dwarf planet movements. The interactions of gravity between Pluto, Neptune, and the other massive planets like Jupiter and Saturn are key to preserving a delicate equilibrium that prevents major disruptions. However, this stability is not guaranteed forever, and the forces at work may gradually change over the course of billions of years, leading to outcomes that are impossible to predict with complete certainty. While Pluto's orbit remains stable for now, the possibility of future disruptions is a compelling reason to continue studying this distant planet. The gravitational interactions between the planets are constantly shifting, with every orbit influencing the others in small but potentially significant ways. Even though the current gravitational relationships are enough to keep Pluto and Neptune on separate paths, that balance is far from permanent. The forces involved in maintaining the current state of stability could, over time, change in ways that might result in an eventual encounter between these two worlds. One of the exciting aspects of this area of research is the ongoing advancement of our technological capabilities, which provide new insights into these cosmic puzzles. As computing power improves, simulations become increasingly sophisticated, enabling scientists to model the complex interactions of celestial bodies with ever greater precision. These advances could potentially reveal new patterns or factors that we have yet to consider, helping us refine our understanding of the forces that govern the movement of planets and dwarf planets. Additionally, as space exploration progresses and new missions are launched to study distant objects, we may uncover more data that will shed light on the long-term evolution of our solar system. The study of Pluto, once relegated to the status of a minor object at the edges of the solar system, has now become a key focus for astronomers and planetary scientists eager to unravel the mysteries of the outer reaches of space. Through continued observation and research, scientists hope to learn more about how Pluto's orbit evolves and how it interacts with Neptune and other massive bodies in the solar system. Beyond the potential for a collision, the case of Pluto and Neptune raises broader questions about the stability of the solar system as a whole. The gravitational forces at play are not isolated to just these two planets. Every object in the solar system, from the smallest asteroid to the largest gas giant, plays a role in shaping the movements and interactions of other celestial bodies. Understanding how these forces work together to maintain balance, and what could happen if that balance were to be disturbed, is a fundamental question for astrophysicists.